Good morning. Today we're going to continue looking at probability, and specifically today we're going to look at experimental probability. But let's do a little bit of review first. So this says you roll a standard number cube once, so something with 6 numbers on the sides, 1 through 6. Find the probability of each event as a fraction, a decimal, and a percent. So what's the probability of rolling a 4? Well, how many 4s are on the side of a die? If you roll a die, there is exactly 1 4. And if you look at all the sides, there are a total of 6 sides. So only one of those out of the 6 satisfies the probability that they're talking about here. So there's our fraction. If we write that as a decimal, we're doing 1 divided by 6. That's what I'm putting in my calculator, 1 divided by 6, and I get 0.167 because I like rounding to 3. And then as a percent, I'm going to move that decimal 2 to the right and I get 16.7%. Now we've got, what's the probability that it's a multiple of 2? Well, a multiple of 2 would be something like 2, 4, 6, etc. And these are the 3 numbers, if we look at a die, that are multiples of 2. So out of my 6 sides, these are the 3 that satisfy that. So we've got 3 out of 6, and we always want to put that in simplest form. So that would be 1 out of 2. And then there's our fraction. If I do 1 divided by 2, we'll get 0.5. Change that to a percent means moving the decimal 2 to the right, and so we would get 50%. Remember that when it's 0.5 and we move that 2 to the right, we're going 1, 2 over. And so we need to fill in that space. Don't make the mistake of putting 5%. So 50%. There's our 3 ways of writing it. So what is the probability of rolling a 5? This is something that we would do in class. This is something that you can simulate right now. If you have a die around, that would be really great. But what's the probability of rolling a die? Well, it's 1 out of 5, or sorry, 1 out of 6, or 0.1, we just said it was 0.167. But then what we would do in class is pass the die around, and each person rolls it once. So we have, if you include me, 13 people. Maybe out of 13 people, we'd get 3 people rolling a 5. I'm just throwing out a number there. So if we look at that, we'd write the ratio of 5s rolled to the number of rolls, and that would be this right here. And then repeat the process. Maybe the second time around we only get 2 out of the 13 roll a 5. In class in the past we had, I think the lowest we had was 1 out of 9. Well, including me, 10. The highest that we had was last year. We had, I think we had 5 out of, how many did I have? 12 last year, including me, 12. So you can see that if we pass a die around and each roll it, we're going to get very different numbers. We're not going to get 1 out of 6 perfectly each time. So what do you notice about the probabilities? They're going to be different, usually. And it's not always going to equal this 1 out of 6. So experimental probability is probability based on experimental data or observations. Or in other words, the probability of an event happening is equal to the number of times an event occurs over the total number of trials. So here, this answer is our theoretical probability. We know that there are 6 sides, there's 1 5, so theoretically, out of every 6 people who roll the die, 1 person should get a 5. But these numbers, this one, and this one, and this one, and this one, these are all experimental probabilities, where we say, okay, now that, like maybe if we look at this one here, we say, okay, now everybody's rolled the die 1 time. 2 divided by 13 is 0.154. So this is our new probability. This is our experimental probability. And notice that it's different from our theoretical. So experimental probability is looking at what has happened, and we're going to use that to predict what happens. So Amy flips a coin 6 times and gets 25 tails. Now, if I just said, what's the probability of getting tails? You would say 1/2 or 0.5, because either you get heads or you get tails. There's only 2 outcomes. But this time we're going to use what's happened. So we're going to say the probability of getting tails, again, is equal to the number of times that she did get tails over the number of times she flipped the coin. Well, if I do 25 divided by 60, I get 0.417. Now, the theoretical probability is still 0.5 because theoretically, every time she has a 50-50 shot of getting tails versus heads. But based on what's happened so far, what she's done, she's flipped the coin 60 times and she's gotten 25 tails. Based on that, she's going to say, well, actually, my probability goes down to 0.417 instead of 0.5. Is that accurate? I don't know. So Alex has 16 pairs of socks in her drawer, 6 white, 7 black, and 3 purple. Find the experimental probability of randomly picking a pair of socks that isn't black. So what we would need to do is say, all right, she's got 16 pairs of socks, and 7 of them are black. So the probability of getting black socks, actually this is theoretical probability, but that's okay. Black socks is 7 out of 16. So that would equal 0.438. Now, this is actually, I didn't write this question well, but this is not actually experimental. This is more theoretical, because to be experimental, it would have to say Alex has 16 pairs, this many, and this many. She drew 5 socks out and got 2 of them to be black. And it would have to show that she had performed this experiment at least one time. So I apologize for that. I'll make sure that your questions in the future are better worded, but it's still a good practice for us looking at what are we trying to find. We're trying to find, oh, I made a mistake. That isn't black. And this is where reading comes in handy. I don't always read well. So we're going to put not black. So we can actually use our complements here. We know that the probability of getting one that's not black is this, or of getting black is this. So to get a probability of it not being black, we would take 1 minus the probability that it's black. So if we do that, we would get 0.563. And there we go. All right, so a survey of 125 students at a middle school shows that 45 of them have a pet dog. So there's our experiment that they actually took this survey. They could repeat this survey and ask a different 125 students. They didn't ask all of the students at the middle school. They only asked some of them, and that's what makes it experimental probability in this case. So it says that 45, or we want to know the probability of having a dog. So probability of having a dog. We see that 45 out of 125 people at the middle school in this sample survey had a dog. So if we do 45 divided by 125 in the calculator, we should get 0.36. So this is our experimental probability. Again, we could take this survey at the same middle school again with a different 125 students, and we might not get the same probability. And that's where the difference comes in of experimental versus theoretical. So then it says, about how many students would you expect to have a pet dog if you surveyed 275 students? So what we're going to do is we're going to say, all right, we're going to assume that this probability applies to everybody. So I'm going to say out of the 275 students, so actually I'm going to rewrite it this way, 0.36 of the 275 students have a dog. All right, and I wrote it that way because what we're going to see happen here is that we have to use multiplication and take this times this. So I'm going to do 0.36 times 275. When I do that, I get 99 exactly. So I can say out of 275 students, I expect 99 to have a dog. And this is what statistics is all about. It's about taking a survey. Now 125 is still a lot of people to ask this question, do you have a dog? But this way we're not having to ask all the students at the middle school. And then we can use our results to write what do we expect to see happen for the whole school. All right, so read this one, pause it, and then come back. All right, so it says that a quality control inspector found flaws in 13 out of 150 sweaters. Find the probability that a sweater has a flaw. So probability that there is a flaw. Well, we know that 13 out of the 150 had a flaw. So we're going to do in our calculator 13 divided by 150. That gives us 0.087. So this is the experimental probability in that sample of the sweaters that had a flaw. So then it says, suppose the company produces 500 sweaters a day. How many will have flaws? So this is something that a lot of companies will use. They want to know how many sweaters do we expect to have mistakes or to have these flaws. So I'm going to take this probability from up here and say 0.087 times 500. And when we do that, we get 43.5. But let's think about that for a second. Does this make sense? Does it make sense that we would expect 43.5 sweaters to have a mistake? No, we can't have half of a sweater have a mistake. So we have to make a decision if we're going to round up or round down. And honestly, I'm not going to be too picky. If you round down to 43 or round up to 44, that's fine. Most companies, what they would do is they would actually round up because they want to assume the worst case scenario. They want to say 44 sweaters will have flaws. And that's what we're going to do. This sentence, you must do the sentence. We're back to writing our sentences because they're asking us a question. How many will have flaws? And so we need to answer the question. 44 sweaters will have flaws. Otherwise, we don't know what 44 represents. All right. That's all I have for today. So head on over to Google Classroom and check out your assignment. Let me know if you have any questions.